in this lesson, I'll give you a very brief introduction to the concept of pH as we understand it in chemistry. You know, you've probably been doing pH determinations for a long time, since about 5th grade at least, where you've probably used pH paper or litmus paper to determine whether something's an acid or a base. You may have been told about pH, that pH in an acid is anything below 7, pH of a base is anything above 7. Now, that was a really simplified way of thinking about acids and bases. In fact, some acids can have a pH above 7. Some acids can have a pH, or some bases can have a pH below 7. So for chemists, it's not the pH that determines whether you have an acid. It's the behavior of the chemical species that determines whether you have an acid. Okay? So even though the behavior is what chemists look at to determine whether a species, a chemical species, is an acid or a base, we still consider the solution acidic if it's below 7, and the solution is acidic if it's basic if it's above 7. Okay? But we're looking more at the behavior of things and whether or not they are going to be an acid or base. Now, an acid then is anything. Now, there's actually 3 major classifications of acids, and we don't have time to go into all that. The only kind of acid we've been dealing with in here are acids that give away hydrogen ions. Okay, and that's our definition of an acid. Okay, it's called the Arrhenius definition. If it gives away hydrogen ions, it's an acid. Okay, so when we were talking about the formulas for acids, they always had hydrogen in the front. Remember that? Acids, the formula of an acid always have hydrogen in the front. And then when we wrote those complete and net ionic equations, we broke out the acid and had hydrogen ions by themselves. Well, that's what acids do in solution. They give away those hydrogen ions. Okay? A base, on the other hand, has an OH, at least a strong base, the kind of Arrhenius base we're talking about here, has an OH on the back side, and it gives away that OH. Okay, so that's the really simplified definition of an acid and base. If acids give away hydrogen ions, bases give hydroxide ions. Okay, and so pH is actually a measure of the amount of hydrogen ions in a solution. pH is a measure of the concentration, really, of hydrogen ions in a solution. pH is a measure of the concentration of the number of hydrogen ions in a solution. So pH is a logarithmic number. Now, anybody in here learn about logarithms in math class? Yeah? You have? What is a logarithm, particularly a logarithm base 10? It's the base 10 logarithm, not natural logarithm. Okay, I know. It's right there on the tip of your tongue, right? Okay. So a logarithm is an exponent. A logarithm is an exponent. Okay, let me get your calculator out, and I hope you have a scientific calculator because you're going to need it in this unit. Okay? And I want you to do this. I want you to find the LOG button on your calculator. Find the LOG button on your calculator. Okay? And I want you to put in parentheses next to the LOG 10, and then use an up caret if you want to, and put 2.5. So that'd be 10 to the 0.2, the 10 to the 2.5 power. That makes sense? Put that in your calculator and tell me what answer you get. All right, so you're trying to put in logarithm, and if you have an Inspire calculator, you're going to need to select base 10. Most calculators don't require that you do that, but Inspire does other kinds of bases for logarithms. So you put a 10 to the 2.5 power. Everybody got that? How many of you done that so far? Okay, what kind of answer did you get? 2.5. And that's because that right there is the logarithm. That right there, that exponent is the logarithm. Okay, on a base of 10, that's the logarithm. Okay, And what it does is it allows you to sort of squeeze together some numbers that really get spread out a long way. All right, lets you see some behaviors that you wouldn't otherwise be able to see in the behavior of some important numbers like pH. Well, pH is the negative logarithm. The P part means negative. H is the hydrogen ion concentration. So the actual math is negative logarithm of whatever the concentration of the hydrogen ion is. And it's molar concentration. Okay? So you put it like this. Okay? Where those brackets mean molar concentration of what's inside. Okay? So this symbolic representation here means the negative logarithm of the hydrogen ion's molar concentration. That makes sense? I hope it makes sense. All right. So then, if we can find the hydrogen ion concentration through some other means, we should be able to predict what the pH is. So we can find molar concentration because we learned to do that in this unit. Okay? So let's say we have, well, let's start with moles. You can do molar mass and find the moles from the mass if you needed to. Let's just say I have 1.47 moles of hydrochloric acid in 0.500 liters of aqueous solution. Okay. What is the pH? Okay, I want you to recall then from the unit where we did equations, we learned to write complete and net ionic equations. And we said that writing complete and net ionic equations were just undoing what we learned to do when we were balancing formulas in the previous unit. Okay, we broke them apart instead of putting them together. Well, we're going to break the HCl apart. Okay, in the same sort of way. I'm going to do it in an equation here. I'm going to say HCl. And I'm going to put it in water, and we're going to break it up into its separate ions. And the separate ions in HCl are H plus and Cl negative. What physical state do I assign to those? What physical state did we assign to it when we're doing complete and net ionic equations? Huh? Not if it's aqueous here. Whatever this is also the physical state here. Aqueous. And the only ones that become separate ions like that are those that are dissolved in water, that are either acidic or ionic. Okay? All right, now, since there's one of these, if this completely breaks up, I get one of those, right? Yeah. So whatever this number of moles is going to give me how many moles of this? If I have 1.47 moles of this, and this completely breaks up, how many moles of that am I going to have? Really? Let's see. 1.47 moles, and Jonathan's right, but let's show why, of HCl. We're going to do a molar ratio. How many moles of HCl do I have in this equation?
1.47.
No, in the equation, how many do I have? 1. And how many moles of H plus do I have? 1. And so when you cancel out moles of HCl and you do the math, you get 1.47 moles of H plus. Does that make sense? Now, we don't have time to get into today strong and weak acids and those different behaviors and things like that, but for HCl and the strong acids, strong monoprotic acids, that's pretty much how it works out for you. Okay. So if I've got that many moles of HCl, I've also got that many moles of H+. Well, now calculating the molarity ought to be really easy because I've got 0.500 liters. I put that many moles of that over liters, I'll have the molar concentration. Do that. Find the molar concentration, please. Okay, so if you take that 1.47 moles of H plus and put it over that 0.500 liters of the H plus solution, and I can say H plus solution instead of HCl solution because once it breaks up, I do have an H plus solution. Okay, then that's 2.94 molar concentration of H plus. Okay, well now I can do the pH, and pH is negative log of that hydrogen ion concentration, molar concentration, so that's negative logarithm of 2.94. Now if you have an inexpensive calculator, you've got to sort of back into this calculation. You have to say 2.94, then press your logarithm button, then press the change of sign button. But if you have a little bit more expensive calculator, graphing calculator, you can probably put it in just the way it appears. Yeah, 2.94 goes in parentheses. And when you are you asking me, do I put this in brackets because that's in brackets?
Yeah.
No. You can put it in parentheses because these brackets are just a symbol that means molar concentration. Okay? So what pH did you get? Anybody? You know, if you're not doing the math, you're not practicing. If you're not practicing, you're practicing to fail. Hope you're doing the math. Yep, that's it. That's it. Did you realize you could have a negative pH?
Yeah.
If you have a strong enough acid of a high enough concentration, you can actually have below 1 in pH. Okay, now we need to round that off. There is actually a third. So far we've talked about two ways to round off when we're doing math. We have a way to round off when you're doing addition and subtraction. That's one way. You have a way to round off when you're doing multiplication and division. That's another way. There's a third way to round off when you're doing logarithms and exponents, but we're not going to take the time to learn this third way. We're going to apply, even though it's not really the right way, we're going to apply the multiplication division rules. Okay? So since this number has 3 significant digits, we're going to assume this one will have 3 significant digits too. And actually it should have 4 if you're using the correct rules, but we'll use the 3. So our pH is negative 0.468 pH. Okay, now pH is not a unit of measurement. pH is not a unit of measurement. So you don't write negative 0.468 pH. pH is a unitless number, but you just have to tell me what it applies to. Now a lot of times people write it that way. They'll say pH 1 or pH 5 or something. But in fact, they should be saying pH is such and such, okay? Because it's not a unit of measurement. So please write it as negative 0.468 equals pH. All right? That makes sense? pH is actually a math process and not a unit of measurement. We often use it like a unit of measurement, but it really isn't. All right, then. If this is a negative logarithm, and we got it from the molar concentration, we ought to be able to find the molar concentration of the pH. Let's see how we do that. Here's what I want you to do. If this logarithm is an exponent, let's put it on an exponent position. Let's take 10, do your up caret, and then parentheses. And since this is a negative of a negative, because it's going to be a negative logarithm, right? So we've got to reverse this. So instead of, you can put negative if you want to. Let me show you what I mean by that. My calculator, I think I can do that. So I'm going to take 10, and I'm going to use that up caret right there. My up caret gives me an automatic exponent. I'm going to open up a parentheses and say negative, another parentheses, and put in the actual number, negative 0.468. Now, a negative times a negative is a positive, right? If you know that, you can make it a positive. If I do the math, then I should get pretty close to the right number. Now, remember we rounded off our answer when we got at the end there, so we're going to have a little bit of a rounding error in the problem. But I got basically, when you round it off, you get 2.94, which is the molar concentration we started with. Does that make sense? So if I give you a pH, you should be able to find the molar concentration of the hydrogen ion. Huh? All right, so let's see. This is how you get pH. Then if we want to find the molar concentration of hydrogen ions, we're going to make 10 the base and take the negative of the pH as the exponent. That's how we find the molar concentration of hydrogen ions.